Hi everyone, and welcome back to the technical workbench once again. This is part 2 Safety Minor Hammer and Morgan videos, and here we have the one that I originally converted back in the 1980s. There was power on light, trip circuit light, trap power light, so when you turn that came on. Not sure they were actually needed really. To keep this video shorter, I'm not going to give the caution about electrical safety. You've had that in video number 1, and I've also taken the screws out of this, so let's get her open without further ado and see what we see. Now straight away, do you remember me saying that I was surprised that the starting position on the other Safety Minor was over at this end, and this one is over on the left, as you can see. So why they did that I don't know. The only difference I can see is there's a metal extension on the sort of plastic arm that goes along. You can see that I've fitted a wire in, and yes, some less than impressive looking additional electronics by myself. Down in the depths there you can see the silicon bridge rectifier that I put in instead of the selenium rectifier. The old selenium rectifier is there. That does the 12 volt uncontrolled, and I seem to remember that was something like 5 amps and 500 volts or something. So that bridge rectifier is perfectly valid. Thing with them is they are more efficient, so because this starts where it starts, you may not get quite such a good fine control. But we can test to make sure it all works. I've already done the electrical safety test such that it is with the impedance meter. Note that that is just a very basic test that most people can do. Proper testing should be done with very high voltage to check that there's no breakdown of the insulation. But I'm fairly confident that we're all right anyway. So give me a minute. I'm going to work out what it was I did back then. All those wires, and there's a small bridge rectifier there. And there's a little trip device at the back there, and there's the big capacitor, and I've got a 300 ohm 2 watt resistor across it. Now bleed resistors, obviously that's what it is. Bleed resistors are valid on large value capacitors, but I'm not sure why. Dad and I were directed by a friend of his who told us what we needed to do, and just got on and did it. Right, so give me a second, let's see what I did. Okay, I'm back. And in amongst all that knitting of wires, I've traced out what it actually is. If you remember this sort of circuit from before, so we've got the variable transformer there, this it's a silicon diode rectifier here, and then there's the smoothing capacitor circuit with the 300 ohm bleed resistor across it. So that comes down from the positive rail of the rectifier through the switch, the half wave switch, to there, much the same, so it allows the effect to go on, so it's switchable again. Then the power on indicator is quite simple really. It just hangs off the output of the rectifier there. There's the little trip at the front, which is a 3 amp one. And now this is the other little bridge rectifier that you see there on the back of the LED. So you can see there's that LED I was talking about that sits on the 12 volt uncontrolled. When the control knob is moved, that's the track one that comes on. That's that one there. And to trip it, let's just do something that I wouldn't normally recommend. Yeah. There's the trip light coming on, so that just indicated a fault. So here we go with the outputs. Let's have a look, see what the minimum voltage is. Oh well, that's not bad. So 0.3, and there it goes up, and see the oscilloscope is just showing the DC ripple now. What do we go up to? 13.5. Do you know what? I think that's slightly less than the other controller. Again, if you look, the arm is biased right over to the side at the starting position to get the minimum start voltage, and then it's quite away from the end, which would have given you the sort of mega speed that some train sets were operated at. But anyway, most people don't use the full power, and don't get caught up on RMS and peak-to-peak voltages. We're monitoring the DC output, and all conventional controllers have a 16-volt AC supply that goes into the rectifier and is then turned into DC and varied either by going through a resistor or, as in we do with this controller, by the variable secondary on the transformer. Right, I'm not happy with the way I'd done that. Didn't think I would be. Not quite as embarrassed as I thought it was going to be. I'm going to strip out all the modifications with the switch position for the capacitor. So the big capacitor will go, bleed resistor will go, all that blue knitting will go. And I've ordered from the H&M website that I showed you yesterday, and I'll put a link in this video, a new black plastic trim to go on here, so I can get rid of the holes as well, and we can put this controller back to its original classical look, but with the addition of the smoothed output. And do you know what I was thinking last night? That it might be worth having a very small fast capacitor across the output terminals, just to be absolutely belt and braces safe and make sure that no spikes can get out. So I'm thinking about something like a 10 microfarad tantalum capacitor or something like that. If I can get sufficient voltage, I'd want to see about 50 volts available on it. Anyway, let me make the modifications and come back and show you what I've done. Hello, welcome back. Well, there's lots of bits and pieces all over my workbench, but you should now recognise from the previous controller's upgrades the capacitor here connected to the negative. Through the switch, the black wire comes there to the positive. That's now switchable on the front with the wave switch. Got rid of the trip, probably getting quite old, and this is the new capacitor, which is a 10 microfarad 50 volt. It's not tantalum, it's another type of ceramic capacitor of some sort, just to act as an additional filter across the output terminals themselves. And you can see the bridge rectifier hiding in there, the silicon one that I fitted. Everything else is much of a muchness. It all works, although the other way around, as we saw. Now then, the top where the LEDs were fitted, well, that's the old bit of trim, which is sort of a metallized thing. I'm going to put it back on for now, but with just a little bit of tape underneath. But I've got a new bit on order, so that will hopefully smarten that up. What I'm going to do is I'm going to put it back together. I'll show you on the circuit diagram this new capacitor and its location, and then we'll do the tests with the oscilloscope and voltmeter and onto the trains themselves. There's the location of the output capacitor, 10 microfarad 50 volt. Right, let's now update this circuit diagram to reflect what's actually in the controller. So there we have it, that's what's now in the controller. Variable controller, rectifier, switched 100 microfarad capacitor for the cordless motors, 10 microfarads put across the output terminals for a bit of filtering, and then our 12 volt DC gun controlled. Nice and simple, the way they were intended. I'm going to do this to yesterday's controller so that it too has that benefit. But now we'll connect this one up and see how it's working. Here we are, it's back in place, tacked in place for now. A bit of tape on to hide the holes so that nothing drops inside the controller. Now then, there's going to be a difference to the output. We're in the full wave only setting, so let's start increasing. Don't quite understand why we've got voltage. I think my battery's starting to go down in the meter. Oh no, I do know why we've got voltage. Oh yes. Can anyone guess? Yes, that's it. That's that 10 microfarad capacitor just discharging very slowly. Nonetheless, let's add some more power in and see what happens. So just turning the controller up, starting at 0.2, and making its way up steadily. But look at the oscilloscope's wave. You're not seeing the ripple because, believe it or not, that 10 microfarad capacitor that we fitted is enough to smooth it out. So you're only going to see that ripple if we were to put a load on the controller. Now I'll just switch the wave switch now. You see the voltages drop up and gradually fall down again. That's as the 100 microfarad capacitor is being put into circuit via the wave switch on the front. So I think we better put a load on this now. And the extremely nice load will be the cordless fitted Great Western rail motor. So we're just going to go, we'll start off in the full wave with no smoothing, but we have got that 10 microfarad smoothing, so let's increase. And now of course you can see the ripple as the rail motor starts its journey. Such a tiny capacitor that it's discharged almost as soon as I return the knob to 0. Go back the other way. So just to let you see, he is moving quite happily up and down. So now I'm going to switch the switch to bring the 100 microfarad capacitor in, and then we'll drive the rail car. And you can see that even less ripple now is apparent. Perfectly good for the cordless motor now. There's no peak to peaks or anything to worry about. This is DC control. The oscilloscope is set to show the ripple. Now if I set it properly, you would just see a line, straight line going up and down the screen indicating the output voltage, but I want to see the ripple because we're looking at that related to the capacitors that we're fitting. So there's the rail motor, working beautifully. And another safety minor. It's almost ready. Well, it's physically ready, but it's a little bit of cosmetics to do, and then it too will join the fleet. And I'm thinking I might swap over to these. I took the little trip circuit out because I've got another idea for that, which I'll tell you about later. So perhaps there will be a small part 3 to this. So there we are. Hope that was interesting. Here's a setup for you. I have my temperature reader now with 26 degrees showing. The controller is just over quarter of the way up, and we're on the smooth setting for cordless. That there is a cordless motor with the temperature sender, temperature pickup strapped to it tightly. And I've just started it. It's 26 degrees currently. Let's see if there's any heat build up in the cordless motor. Just added in a temperature thing for ambient temperature, so it's 23.2. 17.8 outside, middle of August, not very good, is it? Still at 26 degrees. Put another bit of tape on it now. It's really sensitive. If I put my thumb on it, you should see it go up. There we go. That's just the heat of my hand. So it's still running at the same position on the smooth setting. Nice big cordless motor. I like that one. I've got a few ideas for that. Maybe a replacement Terrier motor, something like that. So we're what, 10 minutes in now, and it's still sitting at 26 degrees. Alright, 20 minutes in, and the temperature's actually dropped. Interesting, not expected. So the motor's obviously quite happy. I'll tell you what, let's switch it to the unsmoothed setting, apart from that 10 microfarads. So here the change in the motor. Ready? So here you can go slower. Let's see if the slightly rougher waveform, well, slightly more noisy waveform, heats the cordless motor up at all. My bet says it won't. Welcome back. Oh. 20 minutes more have passed, and it's now at 25, so 1 degree less than it was. I think we saw it drop earlier, didn't we? 23.3 in the room, 0.1 degree higher. and our motor's quite happy. Given what I'm seeing, I expected there to be some warming up, but there's been none, so I don't really see the point in continuing with the test and boring you all with it. But nonetheless, I think I'm confident in saying that the Safety Minor, as modified with the extra smoothing, is no problem at all for cordless motors. Let me go right in close so you can hear it. That's the smooth setting. That's the unsmoothed setting, apart from the 10 mics that we added. Switch again. So all you're hearing really is the speed increase. So I'm going quite fast now, quite fine movements, and still we sit at 25 degrees. Try the other way. No heating effect whatsoever. I appreciate this is an off-load test, but it's very positive, I think. This is the Kerno big wallship. It's a cordless motor fitted loco. This is the cordless setting on the controller I just worked on. And I'm just using this to demonstrate how good it can run. Probably go slower than that. You can see the ripple. Perfectly good. Very impressed actually. It's a lovely loco, isn't it? I have featured it